We have been working with the convolution operation defined by this equation here, and we went over this in a little bit of detail in our introductory video to the convolution operation. We didn't explain this in detail. This equation does have an actual physical significance, which we will explain in future videos. What we did was we sort of set up the recipe when you're going to take the convolution of two functions, how to evaluate it with this integral expression, and we worked through several examples of that. And the reason why the convolution operation is important for the study of differential equations is because of this equation right here. We have a function f of t. Its corresponding LaPlace transform is f of s. We have another function g of t. Its corresponding LaPlace transform is g of s. If we multiply these two together and take the inverse Laplace transform of this product, of course that will give us an entirely different function. That inverse Laplace transform is equal to the convolution of the two functions. That is to say, here we have a function f of t, its corresponding Laplace transform, another function g of t, its corresponding Laplace transform. If we multiply these together, giving us an entirely different function, and we take the inverse Laplace transform, that does not just equal f of t times g of t. What that equals is the convolution of f and t and g of t, whereby the convolution is this integral expression. This is helpful, as we saw. We had, I think, 4 examples of when you're trying to take the inverse Laplace transform of certain functions, and you can express it as a product of two Laplace transforms, then you can use the convolution to obtain the inverse Laplace transform of that product. And we had like 4 examples of that in the previous videos. What we have not done is to prove this equation, and that's what we want to do in this video. Now remember, if we have a function f of t, its Laplace transform f of s is obtained by doing this integral, f of t e to the minus st dt. Or if we have another function, let's call it g of beta times e to the minus s beta d beta with the same limits as this one has, that would be then its Laplace transform will be a function of s, g of s. And again, we have covered this in great detail in our previous videos dealing with the Laplace transform. There's the definition of it. Now, to prove this equation, we are going to make use of this equation. And this equation we did prove in previous videos when we were studying the unit step function. F of s, the Laplace transform of a function f of t, times e to the minus s beta is equal to the Laplace transform of the unit function t minus beta times not f of t, but f of t shifted, f of t minus beta. And again, we've discussed this. In fact, we derived this in our previous videos. We bring it to your attention now because we are going to make use of the fact when we are going to prove this equation right here. So what we're going to do is start off by multiplying f of s times g of s. So we have f of s times g of s. What does this equal? Well, g of s, that was the integral g of beta e to the minus s beta d beta. Beta goes from 0 to infinity. Now this integral is being done with respect to beta. S is being treated just like a constant. So here, f of s times g of s, that's g of s right here. Now f of s is here. There's f of s times g of s. Remember, g of s is the LaPlace transform written like this. But since s is just being treated like a constant, f of s is just going to be a constant. So if we want, we can take this inside of the integral. Like this. Now, we want to recall, here we have f of s e to the minus s beta. But that's equal to this expression. So let's write that out. We have f of s e to the minus s beta, and that equals the LaPlace transform of u, the step function, t minus beta times f of t minus beta. Like this, but we can write this in integral form by using the definition of the LaPlace transform. This equals the integral of this together times e to the minus st dt. T goes from 0 to infinity. This is the definition of a LaPlace transform. Some function times e to the minus st dt with these limits. So this is just this. Now, what effect does the unit step function have? This is always 0 except when t equals beta and either equals beta or is greater than beta. If t is less than beta, this is 0. So the limits aren't really starting from t equals 0, it starts when t equals beta. So we can rewrite this entire integral just simply like this. The integral starting where t equals beta to t equals infinity of f t minus beta e to the minus st dt. And again, this is true just simply because of the effect that the unit function has. And again, we've covered this in previous videos. So right now what we have is that f of s times e to the minus s beta equals this integral expression. So let's take this and write this up here in place of this. So this equals the integral t equals beta to t equals infinity f of t minus beta e to the minus st dt. Now, up here in this integral, for this, we can substitute this integral expression, which means that our product is going to equal some double integral. So now we're going to have f of s times g of s will equal, beta goes from 0 to infinity, times g of beta and this we're going to replace with this. So we're going to have the integral t equals beta to t equals infinity f of t minus beta e to the minus st dt. And then we have d beta. So right now we have that f of s times g of s equals this double integral expression. So let's make some room. We're going to work with this. We're going to erase all of this stuff and put this at the top, writing it now as a double integral. So what we have come up with so far is f of s times g of s equals this double integral. And here, this is the inner one here, so the limits here are for t. T goes from beta to t equals infinity. D beta, its limits go here, and that's beta equals 0 to beta equals infinity. So we have this double integral expression. Now, to appreciate its significance, let's just take a moment and review how the mechanics of multiple integrals, how multiple integration works. Suppose we have this problem. We have two curves, y equals 3 times the square root of x, and another curve, y equals x squared over 9. These two curves intersect when x equals 0 and when x equals 9. And suppose we want to find the area in between these curves. So we could do it one of two ways. We could do it by summing with horizontal strips, or we could do it by summing with vertical strips. If we do it with horizontal strips, we have it like this, then we have to write it as dx dy. Then we have to consider what are the limits on x. So we're starting here, and the way we can think of it is for a horizontal strip, is we have a series of differential rectangles of dimensions dx and dy, and we are summing these in the x direction. The dy, of course, is just constant. And here, summing in the x direction means we're starting at this curve and we're going to this curve. And at this curve, x, if we solve this for x, that equals y squared over 9. So we're going from x equals y squared over 9 to this curve here, where x equals the square root of y over 3. So we're going from here to here, summing all these differential rectangles in the x direction. Then what we want to do is add up the area of all of these strips, starting down here where y equals 0, and keep on going until y equals 9. And there's the limits for y. So that's a multiple integral when we're summing using horizontal strips. Now, if we're going to do it using vertical strips, now we're thinking of this situation. We have a vertical strip of area, and we have these differential rectangles of width dx, height dy, and we're adding up the area of them in the y direction to get the entire area of the vertical strip. So now we're summing in the y direction. And we're doing it going from here up to here. So we're summing from y equals x squared over 9 up to 3 times the square root of x. That will be the area of one vertical strip. Then we add up the area of all the vertical strips, starting at x equals 0, all the way on out to where x equals 9. Now, for our problem here, we have a little bit of a different situation, but it's very much analogous with this expression here. Now notice that back here in our curve, we had an x-axis and a y-axis for the plane. Here, we have a t-axis and a beta-axis. And this equation right here, this double integral, that's the same one as we had written here at the top of the board. Same deal. Now, we're doing this, though, the way this is set up, t goes from beta to infinity. So we're starting with t equals beta. That would be just this diagonal right here at a 45-degree angle. And we're summing then from t equals beta on out to t equals infinity. So we're taking the area here as t goes to infinity, and of course also as beta goes to infinity. Now, we drew this as a horizontal strip because the way we have this set up, this is dt d beta. So we are summing rectangles here in the t direction, starting where? Right where t equals beta, and we keep going all the way on out to where t equals infinity. And we're summing all of them, starting here from where beta equals 0, and then we keep summing higher up to beta approaches infinity. So what we're saying is that this equation that we have derived, this then is commensurate with summing horizontal strips underneath this curve here to get that total area. Well, suppose now we want to sum with vertical strips instead of horizontal strips. So we have this situation. We're starting here, going up to here, and now to get the area underneath here, going all the way on out to infinity, then we take the area of each strip and add them all up. So here we're going from here up to here. So we're summing then up in the beta direction. So now the limits are d beta dt. Beta starting at 0, going up to where beta equals t. And now we're going to add them all up for all these vertical strips, starting here where t equals 0, and keep going on out to where t equals infinity. So for f of s times g of s, it can equal this by summing with horizontal strips, or if instead we sum with vertical strips, f of s times g of s will be this expression. So let's write this one on the board. We have f of s g of s equals, then of course it's a double integral, g of beta f of t minus beta e to the minus st dt d beta. Now the limits are beta goes from 0 up to t. So we have beta equals 0 to beta equals t, and t goes from 0 to t equals infinity. Now we're almost finished. We can rewrite the integral like this. This will equal g beta f of t minus beta d beta e to the minus st dt. Beta goes from 0 to beta equals t. T goes from 0 to t equals infinity. And hopefully this type of integral expression looks familiar to you from what we did before with convolution. See, let's use this to illustrate. Remember how it was set up right from the introductory video. The convolution of f of t, g of t, inside the integral f of t, f of x, g of t minus x, integrating with respect to x. So we do a variable change, as we explained in our introductory video. T is just treated like a constant. And the limits are x equals 0 to x equals t. Well, here we have g of beta, f of t minus beta, d beta. Beta goes from 0 to beta equals t. So that's a convolution. That would be g of t convolution f of t, or f of t convoluted g of t convoluted f of t. They have different integral expressions, but as we demonstrated in previous videos, these are equal to each other, so these are equal to each other. So we can write it as f of t g of t if we want to. Remember what this is. This is f of s times g of s. So what do we have? We have f of s times g of s equals what? Well, we have this integral sign. T equals 0 to t equals infinity. This integral is just this. So we have f of t convolution g of t times e to the minus st dt. But let's look at this integral. This is just the definition of a Laplace transform. We have some function, this, times e to the minus st dt. So, and the limits are t equals 0 to t equals infinity. So what we have is f of s times g of s equals the Laplace transform of f of t convolution g of t. And that is what we set out to prove. It isn't quite in the form that we started with, though. What we had is the inverse Laplace transform equals this. Well, if we take the inverse Laplace transform of both sides of this equation, what are we going to have? I'm going to erase this now. Now take the inverse Laplace transform of each side. Let's write this up here. We have right now f of s times g of s equals the Laplace transform of the convolution f of t with g of t. That's what we have derived so far. Now let's take the inverse Laplace transform of both sides, and we will have the inverse Laplace transform of f of s times g of s equals and that's the equation that we set out to prove right here. So there it is. Hopefully it makes sense. We wanted to take some time and try to prove this in a little bit of detail because this is an extraordinarily important relationship, and in the previous videos we gave several examples as to how to use that expression to solve different kinds of problems where we want to take the inverse Laplace transform. Okay, anyway, that will finally finish it for this video. A reminder, the playlist for all the videos is at the website digital-university.org.